Hello, everyone. So today I'm going to talk about a very famous theorem in graph theory, which is called Matrix Tree Theorem. Matrix Tree Theorem. So this gives us a very quick way to counting the spanning tree in a graph G. And also it's related, actually it's transferred the graph to the linear algebra. Actually, we are going to use the linear algebra to calculate it. So this theorem is actually, we can, because by counting the spanning tree, the number of spanning tree in your graph is very hard, right? Especially for n is very large. But actually, we can use computer to count it for us because we can transfer it into some matrix. And then we can get some result we actually want. Okay, so here is a statement. And I will explain some stuff in it later. It said that let G be a graph. And of course, here we just assume that you understand the sense of the graphs and also maybe some special matrix, but it's okay. And also for here, we assume that this graph should be connected. Otherwise, we don't have spanning tree. The spanning tree is a tree that in the G that contains every vertices. Okay. So let G be a graph which is connected, and let D be the adjacency matrix. Adjacency matrix, and A be the degree matrix. Okay, so then delete the last row and last column in A minus D, get an n minus 1 by n minus 1 matrix, say F. So now we have the number of spanning tree in this graph, which is noted as tau of G, is actually equals to the determinant of this matrix. So this special matrix F. Okay, so see, this is a very powerful theorem in graph theory of counting the spanning tree. And also for here, I will explain some terms. First is D. D is what? D is the adjacency matrix. So D is the matrix with, maybe I would say Dij. D is not that good notation because we might have some degree in later. So let me cross this thing. So D is equals to maybe Aij, which is n by n matrix. And we have that Aij equals to 1 if Vi, Vj is adjacent in the graph G, and 0 if Vi, Vj is non-adjacent in graph G. And also the A, which is called degree sequence, degree matrix, is D1, D2 up to Dn in the diagonal and 0 otherwise. So D1 is a degree for V1, D2 is degree for V2, and so on. Okay, so now let's see some examples. Let's see just one example, it would be enough. So here we have this graph, which is V1, V2, V3. So in this graph, the D is called the adjacency matrix. We will have V1 does not adjacent to V1 itself because we're just talking about a simple graph. So okay, we have 0 for all of those three, and V1 is adjacent to V2, so we have 1, and V1 is adjacent to V3, we have 1, so 1, 1, they are symmetric, and also we have V2 not adjacent to V3, so we have 0. So this is the adjacency matrix for this graph G. Let's see, this is G, and also we have the degree sequence, the degree matrix. Degree matrix should be V1 is 2. V2 is 1, V3 is 1, and 0 otherwise. So now A minus D will actually get this matrix, which is 2, 1, 1, minus 1, minus 1, minus 1, minus 1, 0, 0, 0. Then the F should be the matrix deleting the last row and last column for this matrix. So we'll have 2, minus 1, minus 1, 1. Okay, so now evaluating this the determinant, we'll get 2 minus 1, which is 1. So that means the spanning tree in this graph, just 1. And of course, this graph is very easy, very simple. So you can obtain the number of spanning tree in this graph, just 1. But for larger n, we might need some more countings, and you might make some mistakes. At that time, we need using this theorem immediately to obtain the number of spanning tree in this graph. Okay, so that's all for today, and thank you for listening.